All right, we're going to move into the second part of our nuclear reactions unit, and we are going to start talking about half-life and decay rates, okay? So I'm going to go through this PowerPoint with you and fill out your notes sheet for you. So make sure you've got your notes book, and I am on the where it says radioactive decay, that worksheet. So here we go. So it says radioactive decay rate. So it's impossible really to predict the exact moment when any particular nucleus will decay, but it is possible to predict how much time it will take for half of the nuclei in a given radioactive sample to decay. All right. And so what is half-life? Half-life is the time it takes for half of the atoms of a radioactive substance to decay. So, and it's usually given to you in a number. You can figure out different things based on the information that you get. So, it goes ahead and tells me the half-life of radon, and it's radon 222, is 4 days. So what that means is every 4 days it sheds half of its half of the element. So at 0 days, I start with radon 222. Okay, and so I'm gonna say that this would be all filled up. So I've got 100% is radon 222. Okay, after 4 days, so this is 4 days, I'm gonna have half left, which is 50% or 1/2. Okay, so it's going to take up half the container. I'm guesstimating. After 4 more days, which is a total of 8 days, I've got half of the half. So half of 50 is 25%. All right, or we would say 1/4. Okay, it's about a quarter of this container. After 4 more days, so now I'm at 12 days, I've got half of 25, which makes 12.5%, and half of 1/4 is 1/8. Here's what you can do if you don't understand that. 1 divided by 4 divided by 2 gives you 0.125. So it's 12.5. That's where that number's coming from. And if I take this percentage and I put it into a decimal, that would give me that. Okay, so I'm just down to here. And then notice I've got it's decaying into another substance. So this is how much radon I have left. After 4 more days, it would be 16 days. I'd have half of 12.5, which would be 6.25%, or 1/16 left, which is just a little bit right here. Okay, and so it's slowly decaying off. All right. So the nucleus after it has been decayed is actually called the daughter nucleus. Okay. All right, so let's look at these. All right, it says you just won $1,000. Okay, but you can only spend 1/2 of it in 1 month. So after 1 month, if I start with 0 months, I start with the full amount, and then I continue to divide the amount in half. Remember, my half-life would be the time it's taking. So I'm not going to double it by 2 every time because it's a constant 1 month. So after 10 months, I would end up with like hardly any money. Okay, end up with hardly any money. All right. Next thing, here's another example with cobalt. Okay, so cobalt has a half-life of 5.3 years. So every 5.3 years, cobalt decays by half. So what I start with is the parent material, that's cobalt 60, and what I end with is the daughter material. All right. So look, after 5.3 years, I'm at 50%. After 10.6, because 5.3 plus 5.3 is 10.6, I'm at 25%. Okay. Of my parent material. Now, notice my daughter material is 75% because I'm always going to have 100%. After another half life, which is another 5.3 years, I'm at 12.5% of my original material. And then the rest of it would be my parent material. Okay. And then after another half life, I'm here. And so, really, you're going to reach like a limit. You're never going to get to 100%. But basically, what happens is it ends up decaying and it basically turns into that element. Okay. So it says, and we just went over this, the nucleus left after the isotope decays is called the daughter nucleus. Each element decays into a new element. Okay. So if I look at this diagram right here, I have a parent nucleus. You start with parents. It pushes off an alpha particle, and then what is left would be my daughter nucleus. Okay, and so here's another example of carbon 14. Okay, so the blue grid represents the quantity of carbon 14. So each time we click, one half-life goes by and it turns red. So after one half-life, notice I'm completely in half. Okay, so now I'm looking at this amount of blue. So I've got 8 squares that are blue. After another half-life, there's only 4 squares. So I'm taking this amount and I'm dividing it by 2. So if I've got 4 squares left, now divide it by 2, I'm going to be left with 2 squares. And after another half-life, I should be left with just 1 square. Okay. Looking at the radioactive decay of carbon-14, now I can look at this diagram, this graph down here. Okay. Look at this graph down here. All right. So this graph down here is talking about carbon-14. 100% is how much I start with. So I always start with 100%. 100%, I'm starting with 10 grams. Now, after one half-life, I'm left with 50%, which in this case would be 5 grams. After 2 half-lives, that was at 25, I'm left with 2.5 grams. After another half-life, so now I'm at 3 half-lives, I'm at 1.25, okay? And now look at this half-life. It's really, really large, okay? It's really, really large. So let's see. Let me ask you this. How many years does it take to get to 3 half-lives? Or let's do this. How many years does it take for carbon-14 to decay to 1.25 grams? All right. So if I start with 10 grams, after one half-life, I'm at 5. After 2 half-lives, I'm at 2.5. After 3 half-lives, so 3 half-lives, I'm at 1.25. Okay. 3 half-lives, this is 1 half-life. I need to multiply this by 3 or add it to each other 3 times. So 5, 7, 3, 0, 3. That gives me a large number. This is how many years will have elapsed. That's how many years it would take to get this amount, which is a long time. Okay. Half-lives. It says some radioactive isotopes decay to stable atoms. Some require more half-lives. And right here, we're going to write vary widely among the radioactive isotopes. So look at this chart over here. I've got 12.3 years, 0.5 seconds. Okay. This one takes years and years. Uranium takes years and years to actually decay. So it really varies from element to element. Okay. All right. So really, we can use these for medical applications. We can look at different things to see how they're used. And these are a couple of things. Okay. And now let's look at this graph. Okay. This is not in your notes. It says, what is the half-life represented in this graph? Okay. If I want to find out the half-life, I need to see how many years time has it taken for this to get to 50% or half of the original amount. So I'm going to come right here where this blue is. I'm going to come down. All right. This is 1, and this is representing time. So this is 1 million years is the half-life. After 2 million years, there's 2 half-lives. All right, that's why this answer is right there. All right, I want you to pause the video and see if you can answer these 4 questions right here, and then come back and check your answers. All right, so all right, the question is, it's down here. How many half-lives does it take for uranium-238 to decay to only 12.5%? First thing I want to do is, if I come back up here, I need to set up a chart for you, so when you see it, you understand kind of how you're going to set these up. All right, so anytime we have half-life, we're going to make a chart. My chart's going to have some of the same information in it, okay? I'm going to have the number of half-lives. I'm going to have the time, which is going to vary. I'm going to have the percent, and I'm going to have a fraction. Okay, so number of half-lives, percent, and fraction will not vary from thing to thing, okay? So I always start off with number of half-lives as 0. If I start with 0 half-lives, I have 100% of my original substance, okay? My fraction for 100 is 1. 1 whole is 100%, okay? I'm going to take time out just for now, okay? And then we'll add it. I could also have on here amount, and we'll look at these a little bit later when we get into a little bit more specific stuff. After 1 half-life, I take my percent, I divide it in half. That gives me 50%. 1 divided by 2 gives me 1 half. After 2 half-lives, percent, take this one, divide it by 2, it's 25. Divide this by 2, 1/4. All right. 3 half-lives is 12.5%, 1/8. And it will always be after 3 half-lives. 12.5 always comes after 3. All right. 4 half-lives. And we'll stop at 5 half-lives. All right. So after 4 half-lives, I am at 6.25, or 1/16 of my original. And I have, if I'm looking at 1/16 of my original, I actually have 15/16 of my daughter present. Okay, so if I ask you, where is 7/8 of my new substance occurring, that would be at 3, because if I have 1/8 left of my original, that's happening at 3. All right, so come down here, 6.25 divided by 2, that gives you 3.125. And that's 1/32. Okay, so now we can go back to our chart. And our chart down here asks us, that's a little blurry. Okay, it says, how many half-lives does it take for uranium-238 to decay to only 12.5%? Anytime, I'm going to refer back to that chart. So the answer for this one is going to be 3, after 3 half-lives. Okay, so no matter what, 1 half-life is 50%, 2 is 25, 3 is 12.5. All right, how long did it take for uranium-235 to decay to 6.25%? Okay, so I'll come back up here to my chart. So I would always make this chart on your paper. 6.25% is 4 half-lives. So let's look. 100, let's read this. Amount of remaining, this is 50%, or this is my percentage. All right, this is 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. So how long did it take? I need to see how long it took. So I come over here, I get my ruler because it's really hard to see. And I connect the dots. This is going to be 4 half-lives right here. Okay, and I'm looking at time. So I would say 18,000 million years. Make sure you read the axis. Okay, how much uranium is still left over after 4,500 million years? So that is right here. This is 1 half-life. So 1 half-life, 2 half-lives, 3, 4. If I only have 1 half-life occurring, after 1 half-life, 50% is gone. So that means 50% is remaining. Okay, and then the last one says, in fraction form, how much of the original sample of uranium-238 is still left over after 2,200 million years? So that would be, this is 4, this is 5. Okay, on my sheet, that's 1 over 32. It says is still left over, so that would be 1 over 32. Okay, it's not the new substance. If I was referring to the new substance, it would be 31 over 32. So make sure that you can read the graph. All right, going to my next one. Okay, this is the type of table that I am referring to. It says, for example, if we suppose we had 20,000 atoms of radioactive substance, if the half-life is 1 hour, how many atoms of that substance would be left after? So I set up a chart. I'm going to put in what I feel like is relevant. Half-lives, atoms remaining, percent of atoms remaining, time, and then the fraction, okay? So I always start with 0 half-lives, which means I have all of them remaining. And all of them, in this case, would be 20,000. That's what I start with. Percent remaining is 100%. My time has not happened. It's going to be 0. And my fraction is going to be 1 when I start. Okay. To go have 1 half life, I'm going to take this number and divide it by 2. So after 1 half life, I've got 10,000 remaining. What percent is that? 50. How much time has elapsed? I have to look up here. The half-life is 1 hour. So 1 hour has elapsed. After 2 half-lives, take this number, divide it by 2. 5,000. Okay. And then I have 25% remaining. That gives me 2 hours. Now, I'm not multiplying as I go through. You'll see the next one. So after 3 half-lives, I've got 2,500 left. I've got, divide this number in half, 12.5%. And notice, this is not going to be 4 because remember, my half-life is 1 hour. So I'm adding this column. This is going to be 3 hours. Now to do our fractions, this would be 1, then 1 half, 1/4, and 1/8. Okay, so the question is, how many grams of iodine 131 would be left after 20 days if you start with 25 grams? Okay, so let me switch back over here. All right, and you've got the question. Now I've set the chart up for you. Okay, when you kind of keep going through, you need to start making your own charts. So, and you're not always going to use the every part of the chart. So like the fraction's not here, the percent isn't here, but the fraction and percent is always going to be the same. So it says how many grams of iodine 131 with a half-life of 5 days would be left after 20 days if you start with 25 grams. Okay, so I started with 25 grams. I have 0 half-lives and 0 days. And then I can fill this in. 1, 2, 3, 4, 5. And I'm only going to go to where 20 days will be. Okay? Because there's no point. Now, I can start filling in my time because it says the half-life is 5 days. So after 5 days, I would have half of this amount. Half of 25 divided by 2 is 12.5 grams. Another half-life would be, and I'm not I'm adding 5 to 5. This would be 10 days. The biggest thing is people want to multiply these too much, okay? So this gives me 10 days. So 12.5 divided by 2 gives me 6.25 grams. Okay, another half-life, so 5 more days. I'm at 15 days. divide my other number by 2. So 3.125. And I'm not dropping off. Now, I'm at 20 days. So I'm going to stop here because my question says after 20 days. All right, divide 3.125 divided by 2. And I'm going to round 1.56. So how much is left? 1.56. It's important that you put the unit on it. Grams. Okay, so what I want you to do is I want you to pause the video and I want you to finish the other 3 questions and then come back and check your answers. All right. Now here we go. It says, how long will it take 600 grams of plutonium-239 to decay to 18.5 grams? So I start with 600 grams. My time is going to be 0, and I'm looking at years. My 0, 1, 2, 3, 4, 5 number of half-lives passed. Okay, and it's decaying to 18.75. So I'm going to start. I'm dividing this in half. 300, 150, 75. I had to pull my calculator out. 37.5, 18.75. Okay, so I know that at 5 half-lives I need to get there. So now I'm going to go plug in and look at my years. So after 1 half-life, that's 2,400. Then I go to 4,800. 7,200. And I'm adding 24,000. It's not 100, 24,000 every time. 96. Okay, so remember, I still want to answer the question that it's asking for. My question asks for how long, so I'm looking for time. So my answer to this question is 120,000 years. Okay, and then the last one that you had says, potassium-42 has a half-life of 15.5 hours. If 13.125 grams of K42 remained undecayed after 6.2 hours, what was the original sample size? So this one I'm actually working backwards. So I need to kind of treat this one a little differently. I'm going to go ahead and plug in my half-lives. Okay, I can do my time, 0, because I always start with 0. In this case, it's hours is my unit. Okay, and it says after 62 hours. I know each half-life is 15.5, so 1 half-life is 15.5. After 2 half-lives, there's 31 hours. After the next half-life, it's 46.5 hours. And after another one, it's 62 hours. Okay. So now I'm kind of working backwards as I do this. So it says if 13.125, so this number right here is 13.125. And I got that because it remains undecayed. So I have to multiply this. I'm moving back up to figure out what my original sample size is. So 13.125 times 2. This would be 26.25. Multiply that by 2. 52.5 times 2. So you're just multiplying every one of them by 2 times 2. Okay. So I should have started with 210 grams. So my answer would be 210 grams. Now, look, check yourself, okay? 210 divided by 2 gives me 105. 105 divided by 2 gives me 52.5. You can kind of make sure that you started. So this is the answer to the question. Okay, so now what I want you to do is I want you to go to TeacherMade and complete the 10 practice questions from today and make sure that you come back and check your answers. Okay, using this chart makes it really easy to not get it incorrect. If you don't use the chart, there's no guarantee with as much math as you're going to have to do that you're going to get it correct. So take the time and use the chart.